Okay, we're talking about estimating probabilities. This is the first of two videos, and we're looking at situations of random experiments which don't have equally likely outcomes, so things that aren't predictable. So it's not like rolling a fair die or tossing a coin. So in particular, we're looking at these sort of scenarios here. Okay, so less predictable things in a sense. There's a few ideas. There's the idea of subjective probabilities, where people just assign a value just based on experience. So maybe a sports journalist might say that a certain team has a 50% chance of winning the grand final or the premiership. So that's very subjective, which basically means it's based on somebody's opinion, which may or may not be reliable. So that one's only used sometimes, especially for serious matters. The probability from data is more reliable, and it's a way of estimating an unknown probability. So basically experimentation is used with in the means to get the data. So in this case, these experiments, random experiments with many trials, happen in the data, and the results are recorded. This information is used as a sort of probability then to estimate the chances of the event happening again in the future. So it becomes, in a sense, a probability, this estimate. And a word for this is called the relative frequency. So make sure you make note of that, the relative frequency. This is the formula for relative frequency. That should look familiar because you've probably seen it in junior. And also, the relative frequency resembles the basic probability of event formula. So the number of times an event A occurs over the number of trials is the relative frequency of the event. So that should seem familiar because it's very similar to our formula for theoretical probability in simple situations. So an example of this that you see quite a lot is the case of the drawing pin. So drawing pin is something that's more likely to land on its side like that, or like that, and you can intuitively see why it's more stable that way. The effect of the leverage and the curvy top of it makes you sort of assume that it's going to land more likely on the side than the top. It can land on its top, or what they call on its back. It is possible, but it's less likely. Though this graph disagrees with me, this graph is actually an experiment showing the probability of it landing on its back. So perhaps I'm wrong about that. Maybe it's more likely that it is going to land on the back. It's been a while since I've actually done the experiment, so perhaps it is more stable like that. So the point is that if you do this experiment a certain number of times, and then you increase the frequency, so if we throw a drawing pin 20 times, we might get 8 out of, well, that would be 16. If it was right on there, it'd be 16 out of 20, or a 0.8 relative frequency. But it's coming down, and then it seems to stabilize about a certain value. And so with a lot of trials, a lot of goes at this, we get values that tend to hug a certain imaginary line, or they tend to correlate with a certain value. And that's significant. So they would have done the number of times to get the relative frequency of the point up. They would have done the number of times the pin landed with the point up over the number of trials, which is the same as that formula there, just an application of it. And in general, when the same experiment is repeated many times, perhaps you could call 140 times many. Again, that's an open to opinion thing. So when we repeat it, like plenty of times, the relative frequency the value we get here becomes what's called a point estimate. And the more times you repeat the experiment, the more trials you have in the experiment, the better the point estimate is. The point estimate becomes more reliable. So when the number of trials is sufficiently large, the observed relative frequency of an event becomes close to the probability, which what they mean there is the theoretical probability. So the probability of an event A is approximately equal to the number of times A occurs over the number of trials, and that's provided we have a large number of trials. Large number of trials are sometimes linked to this phrase called the long run, and a large number of trials provides reliable long run probability estimates. So another way to estimate a probability is to take a random sample. So this is different to an experiment. So for example, you could get, you can imagine the big jar of jelly beans, and if we want to know how many of a certain color or the probability of a certain color, e.g. black, we could just randomly choose 50 jelly beans out of the jar and then count them up, use proportion, calculate the relative frequencies, and use that as our point estimate. So provided you could argue whether you think 50 is a lot or not, but you certainly need to take plenty of samples for your random sampling, because again it's a bit like that long run probability estimate. You need a large number of trials, or in this case be a large number of items in the sample. Another way, which we'll look at in the next video, is simulation. It's a way to model a random experiment such that the outcomes closely match the real world outcomes. A simulation can be done digitally, but it can be done physically as well. Simulation does not involve repeating the actual experiment. More complex probabilities can be estimated via multiple trials of an experiment, which gives an approximation, and the idea is for it to be fairly quick and easy. So in summary, when a probability is unknown and it's a random situation that's not very predictable, so it's not simply tossing a coin, it can be estimated by relative frequency using our formula here, the number of times event A occurs over the number of trials, and that'll give us an estimate, an estimate of the probabilities, provided we have a large number of trials. Whichever method is used out of the ones I mentioned above, which were the simulation, the experiment, the subjective, which is probably not one to dwell on too much, and lastly the random sample. Whichever method is used, the same rules hold. So probability of an event has to be 0 or bigger for each event, and of course probability as a decimal is between 0 and 1, and the probability of the universal set is 1. So basically the universal set has all the sample space in it, and the sum of the probabilities of a random experiment equals 1. So all the possible probabilities of all the possible outcomes has to be added to 1, and that's linking to this statement here as well. The probability of the universal set is equal to 1.